Okay, let's dive into this explainer. We're looking at the Saga pattern today. It's honestly the exact thing that separates junior developers from senior backend engineers. We're talking about how to design systems that actually handle failure gracefully, instead of just, collapsing under pressure. Because when you make that jump from building simple monolithic apps to orchestrating massive hyperscale microservices, the rules of the game completely change. You're no longer just writing code. You're managing the unpredictable, chaotic, emergent properties of a distributed environment. So let's get right into the core of what makes these systems truly resilient. Picture this. You've built what looks like a totally robust system. A user clicks a button, which fires off a complex workflow behind the scenes. Step 1, finishes perfectly. Step 2, validates smoothly. Step 3, completes without a hitch. But then, Step 4, fails. What do you do now? Maybe it was a sudden network timeout, or an API rate limit you didn't anticipate, or maybe a downstream server just literally died. This is that visceral, pit-of-your-stomach production nightmare that every backend engineer eventually faces. You can't just pretend the first 3 steps didn't happen, but you also can't move forward. Let's map this exact scenario out in a real 4-step pipeline. First, we extract data from a document. Second, we validate it against our business rules. Third, we write a decision record to our database. And finally, step 4, we trigger a downstream system notification. But as we said, that 4th step fails. Without explicit system design, you are completely stuck. That decision record, it already exists in your database. If you just retry the whole pipeline from scratch, you're going to write a duplicate record. But if you do nothing, you leave the system in this broken, intermediate state where the record exists, but the downstream system is completely unaware of it. And this brilliantly illustrates the fundamental difference between monolithic and distributed architectures. Back in the day, in an old-school monolith, this wasn't really a problem. You just rely on your relational database's ACID properties. You'd wrap all 4 steps in a single database transaction, and if step 4 fails, you just execute a simple database rollback. Boom, the whole thing is undone like it never happened. But once you cross network boundaries into distributed microservices, that safety net absolutely vanishes. Now you're dealing with eventual consistency, completely unpredictable network latency, and the absolute certainty of partial failures. A standard rollback simply does not work across distributed APIs. The safety net is gone, and you have to engineer a new one. This is where we introduce an indisputable law of backend system design, the Saga pattern. Here is the rule. In a distributed system, every single step that produces a side effect must be paired with a compensating action that explicitly undoes it. You can't just rely on some magic database rollback anymore. You literally have to engineer the rollback yourself. The Saga pattern acknowledges that, hey, failures are inevitable, so it dictates that your architecture must have an automated, predefined escape hatch for every single action it takes. It's really the absolute only reliable way to handle partial failures when you're dealing with multiple independent services. So let's apply this directly to our broken document pipeline. Step 4, that downstream notification failed, right? Well, because we designed this using the Saga pattern, the system immediately executes the compensating action for step 3. It explicitly deletes the decision record it just wrote. By systematically undoing the side effect of that last successful step, the system returns itself to a perfectly clean, consistent state. Now the entire workflow can safely retry from the very beginning. No risk of creating duplicate records, no triggering double notifications, and absolutely no corrupting the database state. Now, what's really interesting about this is how these exact same principles apply to the bleeding edge of tech, multi-step AI agent workflows. An AI agent making multiple LLM calls to achieve a goal? That is essentially just a distributed system in disguise. When you look at the mapping, a message queue is just a task buffer between agent steps. An idempotency key is just a deterministic task ID preventing duplicate LLM calls. And the Saga pattern and compensation actions, that's your multi-step workflow rollback when an LLM hallucination or an unexpected API failure breaks a step midway through. If you're building complex AI agents without applying these core distributed systems concepts, you are, frankly, flying blind. Before we go any further, we have to talk about the massive red flags that constantly trap junior developers. These are the exact engineering mistakes that cause those critical middle-of-the-night production incidents. They rely on automatic network retries without any protection against duplicates. They build complex workflows completely missing idempotency keys. They ignore outbox patterns, they execute fire-and-forget asynchronous calls, naively assuming message brokers never drop anything. And honestly, worst of all, they accept partial state corruption, assuming some manual human intervention will clean up the mess later. Let me tell you, at scale, manual cleanup isn't just hard, it's impossible. And that brings us to the absolutely critical partner of the Saga pattern, idempotency. You simply cannot safely implement a Saga without it. Idempotency means assigning a deterministic task ID to an operation. Why? So that no matter how many times a timed out request is automatically retried by the network or by the user hitting refresh, it never results in duplicate executions. It guarantees exactly once semantics in an at least once delivery world. Without idempotency, your retry logic isn't a safety mechanism, it's a duplication engine. Let's ground this theory in a real production example. Think about Uber. A user ends a ride, clicks pay, their cellular network hiccups, and they impatiently mash that pay button again. Uber handles hundreds of thousands of these network drops every single day. To prevent double charging, Uber's mobile app generates an idempotency key tied to that specific trip ID and payment attempt. The backend stores these keys in PostgreSQL with a 24-hour time to live, or TTL, meaning the system automatically purges the memory of that key after a day to save space. If the payment service sees a retry with the exact same key before that time is up, it just returns the original successful result. It doesn't charge the card again. And this extends to the whole workflow, paying the driver, sending the receipt, all safely tied to one idempotent key. Alongside the Saga and idempotency, there's a third pillar to this architecture, the transactional outbox pattern. This is what solves the dreaded dual write problem. Imagine you save a customer's order to your database and then try to publish a message to a Kafka topic to start shipping. Well, if the app crashes right after the database commit, but before the message is sent, your systems are permanently out of sync. The outbox pattern fixes this by saving the event message to an outbox table inside the exact same database transaction as the order itself. It's completely atomic, both succeed or neither do. Then a separate dedicated background process reliably reads that table and publishes the message to the broker. Now, implementing Saga's idempotency and outboxes is certainly not free. We really have to address the explicit trade-offs here. This architecture heavily increases your code verbosity. It adds significant complexity. You're writing extra database tables, compensation functions, dedicated event publishers. It's a lot. But what you are buying with that development time is 100% deterministic reliability. Your system becomes trivial to audit, significantly easier to debug, and remarkably capable of maintaining absolute consistency under massive real-world load. So, the crucial point is this. A rollback is not a strategy, it is a last resort. You must treat database changes as forever forward. When you rely on standard database rollbacks as your primary method of error handling, you are planning for failure in the worst possible way. In high-scale, distributed environments, you need relentless forward motion. You have to design compensations and retries so the system continuously pushes itself toward a resolved, consistent state, rather than just crashing backward and giving up. Let's take all of this and see how it builds into an actionable, senior-level architectural blueprint for your next system. Step 1, define your task schema and validation rules first. Step 2, add idempotency before you even think about adding business features. Step 3, design your Saga and its compensating actions before you wire up the pipeline. Step 4, set explicit blast radius policies. You need to know exactly what requires human approval and what is automated. And Step 5, add tracing and cost attribution from day one, because let me tell you, retrofitting observability into a distributed system is an absolute nightmare. So look closely at these core pillars. If your workflows don't have defined schemas, if they lack deterministic idempotency keys, and if they don't include compensating actions for when things break, you aren't really building a distributed system. You're building a ticking time bomb. The next time you sit down to architect a multi-step process, whether that's processing payments or orchestrating AI agents, challenge yourself. Stop building fragile workflows that assume the network is perfect. Start engineering for failure. It's the only way to guarantee success. So take a hard look at the last multi-step feature you shipped. If your primary database went down right in the middle of Step 3, would your system recover automatically, or would you be waking up at 3 a.m. to fix the corruption manually?